Hi, in this video I'm gonna talk about semiconductors and types of solids, which are the basics to physical electronics. So as we know from high school physics, semiconductor is a material that has the conductivity between insulators and metals. So that's the conductivity of semiconductors. And there are two types of semiconductors actually. One is elemental and second is compound. So elemental semiconductor is basically the semiconductor that consists of one element, and compound obviously two elements. Mostly from the period 3 and 5 from the periodic table. For example, gallium arsenide. And that one, for example, is just silicon. And yeah, that's the basic of the semiconductor, the facts about semiconductor you need to know. And we now move on to types of solids. There are three actually types of solids you need to know. The first is amorphous and polycrystalline. And finally, single. So amorphous is basically just solid that has atoms placed at random places that don't really align. Polycrystalline is divided into several sort of regions in which atoms are aligned like this, but they are not aligned between regions. So for this one and this one, they are not really aligned. And for single, the entire chunk is like aligned atoms, like that. So these are the three types of solids. We now move on to talk about space lattices. So lattice is basically atoms repeated at regular intervals. And a lattice point is an atom in a lattice. And they can be easily generated by translation of one lattice point. So what I mean by that is you have one lattice point here, and you translate it by, say, A, and then say this direction B, and that would be your another lattice point, and you translate that again by A and B, you get another point, and so on. So you create like a lattice like this. So there are sort of like repeated patterns there. And we also need to talk about unit cell. So what is a unit cell? Unit cell is a small sort of section of the lattice, small part of lattice that can be used to generate the entire crystal. So for example, if we look at that lattice we generated, this could be a unit cell because you just use like 6 of these to replicate this entire lattice. And this could be also a unit cell because you can just use more of it to generate. So it can be any sort of small section of the lattice that you can use to replicate the entire crystal. And we also need to look at primitive cell, which is the smallest unit cell. So this is primitive cell, while this is not primitive because it's not the smallest sort of the section you can use, right? And we also need to know that let's look at like 3D now. So let's say that is that looks a bit weird. So let's say that's the primitive cell, and we obviously we would have more of it, right? Just sort of like stacked. Okay, that's not looking great, but they're sort of stacked like that. You see where I'm getting? Yeah. So if that's stacked like that, we can represent every single lattice point as the following equation. R, which is a vector, equals PA plus QB plus SC, and this sort of line means it's a vector, where this is A, this is B, and that is C. So if we, for example, look at this particular lattice point, that would be 2C, right? Because it's 1 and 2C from this point. So that's how we represent each lattice point using vectors. Now the last thing I'm going to cover is the types of basic crystal structures. So again, like the types of solids, there are 3 types. One is simple cubic. 2 is body-centered. And lastly, the face-centered cubic. So simple cubic is just the one with, the classic 8 points like that. And there will be an atom there. So yeah, that's what it looks like. And body-centered is simple cubic. So like that. Plus the one in the middle. That is equidistant from each of the 4 corners. Like that. So obviously there will be lattice points here as well. And finally, the face-centered is the simple cubic. So you have lattice points there at each corner, plus 1 atom at the surface, sort of the surface of each square, like that. And then you have 1 there, like that, and so on for each of the 6 sides, and so on. So yeah, these are the 3 types of crystals, and we're gonna end with an exercise, which is finding the volume density of atoms in a crystal. So, for example, if you have this simple cubic, and we have a lattice constant, which is the length of the edge. Let's call this A. And that's also an A. Also an A. Let's say A equals 7 angstroms, which is 7 times 10 to the minus 8 centimeters, not meters. Then what will be the volume density of atoms, which is measured as something atoms per cubic centimeters. So now we look at the simple cubic. You need to remember that this is a crystal, so that atom at the edge is shared by 8 cubes, because it's gonna look like 1, 2, 3, 4 upper ones, plus 4 in the sort of the low section. So 1 atom there will be shared by 1, 2, 3, 4, 5, 6, 7, 8 if you have this together. So we have 8 times 1/8 of an atom, which is gonna give us 1 atom in this cube. And then obviously the volume of unit cell will be a A cubed. So volume density is number of atoms per volume. It's going to be 1 over a cubed. And you can just substitute this number into here to get the final answer. Alright, so that was it for this video, and in the next video we're going to talk about Miller indices and direction of planes.